Welcome to the edivide video programming lab. What you see here is the setup that's currently running in Oslo, Norway, while this video is taken in UK. Okay, so what you see here is an FPGA board in the bottom. It's an Spartan 6 Atlas board. It provides DVI out. This is connected to the screen in the background. And if you want, you can connect a video stream, which will be connected later to the server, or you can simply take the default background pattern the system provides if no video stream is connected. Then you get this eyes-licking cute little girl. But the picture itself, the bitmap, could also be changed by uploading new pixel values via the COM port. Okay. I change from full screen mode back to the browser mode, and what you see here is the video that's running. And to demonstrate that it's active, I included somewhere a Pac-Man module that's running over the screen. Sometimes it disappears, sometimes it comes back. Okay, here it is. Okay. In the first lab, we will do skin color detection, and that's shown here. So we take the input stream, in this case the background pattern, and we apply the following algorithm that is given by a paper from Peer. And it works on RGB values in the number range from 0 to 255. And if an RGB value is classified as skin, we will emphasize this inside the output stream. Okay. I will start this with uploading the project in our edivide website. So you can, if you log in, go to the remote labs, then you can start uploading a project by giving a job description, like in this case, skin color, for example. Then we choose an institute. So as I mentioned, this is hosted in Norway at the University of Oslo, that's UIO. Then the setup is video processing and the exercise is skin color detection. Okay, this is basically done that you get the right setup, and if you have done so, you go and select your module you want to upload, your source code. So in this case it's skin color. I go on open and on submit, and if we go now down, there is another window further down here. That's actually an output window created from the web server running in Norway, and it's actually a log of the batch job that's running. So what happened in the first step is it prepared a project. This means the original project we provided contains the video input-output, and the student actually uploaded the module that does the skin color detection. And at the moment synthesis is running. This will take a few seconds, and within we can take a small look into the source code. So this is the main function the students have to write for the skin color detection. And I only want to show this to demonstrate that the algorithm we saw can be implemented one by one in VHDL, and the code doesn't look too much different from what people know from C programming or any other language. So you can actually work with integer values, you have compares, you have Boolean operators, you have if then else constructs. So at the first place, VHDL doesn't look too much different. Okay, let's go back to our system here, and we see that synthesis was completed successfully just now. And then we run translate, and most important now is the map phase. In the map phase, the tools actually take the synthesis netlist and fit it into logic primitives of the FPGA, and map does also the placement of the primitives. And this placement is now routed in this pass step, and so between the primitives now the routing is computed, And this was successful, and we go to the bitstream generation. That's running now, takes a few seconds. Okay. In between, I activate our video that's still running with the original background pattern, and the whole process was successful. And if we have a successful project, all important design files will be saved, including the bitstream. And if you go here on refresh, then we see that for the submitted job with our skin color module, we have now a bitstream that we can program. And if I click here, it will take a few seconds. Then the screen will turn black remotely. Let's wait for a second. This is the case when the programming actually takes place. Okay, this is running now. And after successfully programming the bitstream, 1 second, we will hopefully see our skin detection module. And that's what's running here. And the skin colored pixels or pixels that are detected as skin are colored red in this example. I have another example that's Sobel filtering. I will simply start the job and describe what's going on during the time the process is running. Again, this project is hosted, or example is hosted on the UIO system. The setup is the video processing, and it's the Sobel filter. And we change the file and submit the Sobel source file. Open, press submit, and again, if we go down, a new job has been started. It's running now, and we just wait the first few moments. So it's copying now together in a new directory our provided source code plus the submitted source code, and is running the synthesis process. Okay, very shortly what the module will do. Sobel filtering is actually an example for convolution, or also known as the sliding window operator. So consider that we have our background video that's actually a bitmap consisting of several pixels, and pixels come in written top to down, row by row. Okay. And an output pixel is actually computed by looking not only on one pixel as we did for the skin color detection. In this case, we consider also pixels in the neighborhood. And for each pixel, let's say here the center pixel, we not take the center pixel, we also take pixels around in this window. So let's say if we take a 3x3 convolution window, we will consider 9 pixels to compute a value for the center pixel. So as we just get only the present pixel in, we have to think about in the first place how we manage the data movement to get access to also the other pixels in the surrounding. And what we first do is pixels that come here in, so this expresses the data flow, they go through 3 registers, and the 3 registers here basically give me a history over the last pixels. So this is the most recent one, and this is an older one. Okay, but then I also need pixels in another row. So to accomplish this, we need actually a line buffer that stores the pixels that were sent to the system one line before. And the length of this line buffer, the line buffer itself is basically nothing else as a shift register, or can be implemented as a FIFO. The size of this here has to be exactly the size of the screen, or if I compute it only in a window, corresponding smaller. Okay, and as we take in this example a 3x3 convolution window, we have to take 3 minus 1 line buffers to get our convolution window values here. And these are all our pixel values with a history. Okay, if we do this, have done this, we can then take the pixels and apply some processing on them. So in this simple example, we simply put weights on all pixel values and add the weights together. Okay, and the Sobel filtering is, for example, such an example. But it's not necessary that this is a linear transfer function. It could be also something non-linear. For example, you could consider that you sort all the different pixel values, okay, and just take the center one of your RGB values and take this as the output. And this is called median filtering, and this is very good for reducing noise in your picture. Okay, let's go back to our edivide system. So the bitstream generation was successful. I can click here on refresh. I can go and activate the video stream and program the board with a Sobel filter. And that's running here. 1 second. Again, this is, by the way, the programming done LED that's connected from the FPGA. It's off now. And it flashes up again. Wait a second. Now here we are. It's flashing up. And this means the programming was successful and we see the Sobel filtering running on our board. Hopefully you get a small impression of how our lab works, and you are welcome to try it out on your own.